Hey everyone, welcome to episode 2 of the Math Lab, where we put out your burning questions. Is that an even worse tagline than last week? Thank you so much for all of your submissions. We've had some great questions this week again, so we've picked 3 questions. Let's jump straight in. Okay, question 1 comes from M, who says, hello, huge fan, oh thank you, and wondered if you can help. I'll certainly try. Is this a real thing? Half the family says it's a trick and I'm not sure. All right, let's have a look. So what M's talking about is known as the missing square paradox. So we've got this arrangement of shapes and it's going to be shuffled around, and when it's in this new position, we seemingly have an extra square. Now, what is going on? Well, half of your family are absolutely correct. It is a trick. This is not what it seems. Now, incidentally, if you ever see this trick online or anywhere else, and someone says to you, look at this right angle triangle and look at what happens when we change the shapes, tell them to get in the bin. This is not a right angle triangle, and that is where the problem comes into it. If they were to say to you, look at this shape, fair game. If they were to say, look at this quadrilateral, then they're giving you a clue, because that's what actually is happening here. This may look like a right angle triangle, but it very much is a quadrilateral. If we were able to zoom in, what we would see is shape A looks something like this. I'm going to really exaggerate it just to make a point. But the idea is that the slope of that pink triangle and the slope of that blue triangle, they may look the same to our eyes, but they are not the same. Now, there's a few ways that we could work these out using maths. We could either crack out the old trigonometry, or we can just work out the slope of each of these lines. So the way we do that in a triangle is we do the height divided by the base. So in the pink triangle, we've got 3 divided by 8, which is 0.375. And then in the smaller blue triangle, we've got 2 divided by 5, which is 0.4. So we can see that the slopes aren't quite the same. So that's why, far from having a triangle, we've actually got a quadrilateral, a 4-sided shape, which looks a bit like this. Now, what happens when the shape is rearranged is, I'm going to exaggerate again, but our shape looks like this. And if I was to draw an actual triangle in there, you would see that this is that extra space that we've removed with the square. Now, another thing that we can look at that can really clear this up is if we look at the second shape and we look at the top right corner of the blue triangle. So we see that we've gone 1, 2, 3, 4, 5 over and 2 up. And you can see that it looks to be crossing exactly at the corner of a square. Let's do that on the first shape. 1, 2, 3, 4, 5 over and 2 up, and will you look at that? It's slightly beneath the cross. So there's another hint. If you can find a spot on the shape where you can compare, it can be even clearer to see that we've not got the same shape here. So I hope that answers your question, Em. I think the moral of the story, and this is a good one for life and especially for social media, is sometimes we should trust our intuition over our eyes. We know that if we have a shape and we cut up that shape, we're not actually changing the area. So if we see something like this, and there's a few different versions, you might see different shapes to start with, but if you're not changing anything, then you won't be changing the area. So some other trickery is going on. Okay, question 2 comes from Pen Jen, who would like some help with dividing fractions. Now, this is always a tricky area, and I think whenever we're dividing fractions, a lot of us learn that we turn the second fraction upside down and we multiply. Or you might have heard keep, change, flip. And this is all well and good, but it's not very intuitive. Why are we turning the second fraction upside down? Why are we suddenly multiplying? These memory tricks, they can be great, but they fall apart if we don't really understand what we're doing. Incidentally though, if you do just want a trick for dividing fractions, you don't need to turn anything upside down. Let's say we've got 2/3 divided by 1/4. Just multiply diagonally this way. 2 times 4 is 8 over, multiply the other diagonal, you've got a nice butterfly. 1 times 3 is 3. That's the answer, 8 over 3. No flipping necessary. But let's have a quick look at what division of fractions actually is. Now, we need to just start with the division of whole numbers. So let's have a look at 6 divided by 2. Now, one way of thinking about this is, how many times does 2 go into 6? And we can use number bars that look a little bit like this. So we can see we've got a 6 bar here and a 2 bar here, and it's fairly straightforward to see that 2 fits into 6 3 times. So 6 divided by 2 is 3. Now, this actually works just as well for fractions. Suppose we want to do a half divided by a quarter. We can ask, how many times does a quarter fit into a half? So we can get our number bars again. Here's a half bar and here a quarter. We can see that a quarter goes into a half twice. So a half divided by a quarter is 2. Now, this is great, but we probably don't want to be drawing out number bars every time we need to divide fractions, so we need to find a better way. What I'm going to explain isn't necessarily the easiest thing to understand. Don't be surprised if you need to watch this part of the video a few times. You might even need to write it out yourself. But I think that if we're expecting students to divide fractions, they need to have the mathematical maturity to be able to understand why. We can't just be giving them algorithms like keep, change, flip and expect them to just memorize this and you'll be fine. So that's why I don't actually think, if there's any policy writers out there, I don't think that we should be teaching most children how to divide fractions in primary school. For starters, it's not really the most useful thing that you do with fractions. You hardly do that on a daily basis anyway. Secondly, I don't think they're ready to understand why they're doing this. So I don't see a problem with delaying it until senior school. Having said that, I'm not writing the policy and I understand that most kids are going to have to do this in primary school. But I do think that we need to give them a chance at understanding why this works. So, like I said, might take a few watches, but let's give it a go. Now, if you take any fraction, let's say, for example, 1/3, there is another fraction that you can multiply by so that the answer is 1. And that fraction is called the reciprocal. And you get it just by flipping it upside down. So suppose that I multiplied by the opposite, 3/1. Now, if you know you're multiplying fractions, which hopefully you do if you're moving on to dividing, what you can do is you just cancel diagonally, those 3's become a 1, and now we multiply. 1 times 1 is 1, over 1, which is 1. So you see, I multiplied by the reciprocal, the fraction upside down, and I got 1. And this will happen for any fraction. The second thing we need to know is that you can multiply the top and bottom of any fraction to get another fraction that is equivalent. That means it's exactly the same value. You've changed the digits in the fraction, but the amount of the fraction is exactly the same. If you think about a half and 50/100, these fractions are equivalent. They would represent the same amount of a pizza or a cake. What we've done is we've multiplied the top and bottom by 50. So 1 times 50 is 50, 2 times 50 is 100. These are equivalent fractions. They might look different, but they represent the exact same amount, and we can always do that. So that's the second thing we need to know. Now, let's put those things together and have a look at dividing fractions. So let's go back to our example that we were using. 1/2 divided by 1/4. I'm going to write this slightly differently. I'm going to write it as a fraction itself. Now, you probably already know that a fraction is just a division. It's just the top number divided by the bottom number. So 1/2 is the same as 1 divided by 2. Now, I can do that with this division as a whole. Instead of writing a half divided by a quarter, I could write a half over a quarter. It's like a massive super fraction now, but it's exactly the same. So now remember back to equivalent fractions. Remember how we can multiply the top and bottom of a fraction without changing the value. So that's what I'm going to do. But what am I going to multiply it by? Well, I'm going to multiply it by the reciprocal of this bottom bit. Now, don't worry too much about the terminology. Just remember it's the upside down one. It's the one where if we multiply these bottoms, we're going to get 1. So I'm going to multiply the top and bottom by the same. So I'm going to multiply top and bottom by 4/1. Okay, what does this do? Well, if we look at the bottom now, the denominator, what we can see is I've multiplied a fraction by its opposite, by its upside down. That's going to give me 1. That's what we saw at the start. And then at the top, I'm going to have half times 4/1. Now, because a fraction is just top divided by bottom, what this super fraction is now is everything on top divided by 1. Anything divided by 1 is just itself. So now I've got just half times 4/1. And will you look at that? What's happened is we started at a half divided by a quarter, which is exactly the same as a half times the upside down, 4/1. And that's why we can flip the second fraction upside down and multiply, because all these things that we did in between, where we multiplied the top and bottom by the same number, where we multiplied by the reciprocal, we didn't change the value of anything. It's exactly the same. Like I said, that's not the easiest thing to get your head around first time round. It will probably take a few goes. But if you can understand why this works, that can help you to understand why we're using that algorithm, and that will make division of fractions much clearer. Okay, question 3 comes from Preeti, who asks, what is a good way to teach times tables so my kids have it memorised off by heart? Now, we do want our kids to be pretty familiar with their times tables, because when they come to more difficult areas of maths, we don't want them to have to be calculating. We want those facts to be accessible fairly automatically. Having said that, memorising 144 times table facts is going to be pretty soul destroying. Unless you're on some sort of game show where you have the opportunity to win a car, it's not going to be much fun. Luckily, it's not even the best way of doing it. For starters, we don't have to memorise 144 times table facts because of a property called commutativity. Now, this means that it doesn't matter what order we write the numbers in a multiplication, the answer will still be the same. Whether we do 2 times 3 or 3 times 2, the answer is still 6. And what this means is it wipes out nearly half of the multiplications that we have to learn. We're actually down to only 78 multiplications. So it's a bit of a waste of time learning each times table individually. We're going to be duplicating a load, so we shouldn't start there. What we want to do instead is first make sure that kids really understand what multiplication is. So it's not just some abstract 6 times 7 and we don't really know what we're doing. We need to make sure that kids understand that multiplication of whole numbers is really just a shortcut for repeated addition. If we've got 3 times 4, it's the same as adding 4 to itself 3 times. So when you're starting out with multiplication, use blocks or counters to make this really physical. Make sure that they can see what that multiplication is actually doing. Once they've got the hang of this, then we want to start looking for patterns. So for example, when you're working on the 11 times tables, you might notice that 3 times 11 is 33 and 4 times 11 is 44. When you notice this, it's an absolute game changer because it means that you don't have to memorise the whole 11 times table. You've just memorised one fact and you've wiped out all 12 of them. And the times tables are full of these little shortcuts. There are tips and tricks everywhere that can help us to learn the times tables even quicker. We go through loads of these really fun tips and tricks in all of our times tables resources, our course, our ebook, our bookmarks. You can check those all out at sumsofanarchy.com. So once our kids understand what they're doing when it comes to multiplication, once they've got plenty of tips and tricks up their sleeves to help them multiply, they've spotted all the patterns, the next thing we want to do is daily practice. This is the way we ensure the times tables go into their long-term memory, and it's really important to make that practice fun. We don't want them to sit at a desk just drilling multiplication questions. Get it up on its feet, turn it into a game. There are loads of opportunities to practice multiplication in everyday life. If you want more ideas, check out our YouTube video, Times Tables Without the Tears. We cover loads of strategies to help you help your children with the times tables in a fun and engaging way. And if you do that, those times table facts will go into their memories without them even knowing about it. All 78 of them. All right, thank you so much for joining us for episode 2 of the Math Lab. We really hope you enjoyed it. If you did, let us know by hitting that like button and be sure to subscribe to Sums of Anarchy for more maths tips and tricks. Also, leave us your submissions for future Math Lab episodes. If you have a question, feel free to drop it in the comments on this video, or you can message us directly on our Instagram channel, Sums of Anarchy, or email us at sumsofanarchymath@gmail.com. If you've got any suggestions for a new tagline, that will be helpful too. Thanks so much, and we'll see you again for the next episode of the Math Lab.